In this video, I will show you how to graph a polynomial function using the first and second derivative analysis. But first, we will try to get as much information as possible without calculus. So we always consider the domain of the function first, and since this is a polynomial function, then domain of this function is all real numbers. So there won't be any vertical asymptotes or discontinuities. Next, we try to get as many easy points as possible. So we look for the intercepts. To find the y-intercept, we simply set x equal to 0 and evaluate the function at 0. So the y-intercept is 16, and to find the x-intercepts, we set the entire function equal to 0 and solve for x values. So we basically find the x that turn function into 0. So since this is a polynomial function and it is given in factored form, we can easily see that x equals 2 or x equals -4 are the solutions of this equation. Therefore, there are two x-intercepts, 2 and -4. Next, for polynomials, we probably want to figure out the end behavior. And to find the end behavior of a polynomial, we basically have to find the limit of the polynomial as x goes to infinity and as x goes to -infinity. Since the leading term of this polynomial is x cubed, the limit of this entire function is equal to the limit of x cubed as x goes to infinity, so it is equal to positive infinity. Similarly, as x goes to -infinity, x cubed goes to -infinity on the left, so the limit of this function is equal to -infinity. So that tells us the end behavior of the polynomial. And next, we do the first derivative analysis. So to start, we find the derivative of the function. So to differentiate this function, we're going to use the product rule. So we're going to split it into two factors, x minus 2 squared and x plus 4. So the derivative of the first factor is 2x minus 2 times x plus 4 plus the first factor times the derivative of the second one, which is 1. So simplifying this by factoring out x minus 2 gives us the following. So the first derivative is equal to x minus 2 times 3x plus 6. So we can factor out that extra 3. And now we are ready to set this equal to 0 or find the points where it doesn't exist. So since again it's a polynomial, there are no values where it doesn't exist, so we'll only consider the points where it is equal to 0, which are -2 and 2. We construct the sign chart of the derivative by either using the test points or by recognizing that this is an upright parabola, so it is positive on the right, negative in the middle, and positive on the left. So the function is increasing here, decreasing in the middle, and increasing on the right. So at -2 we have a relative max, and at 2 we have a relative mean. So for graphing purposes, we probably want to evaluate the function at -2 and 2. So at -2 we have 32, and at 2 we have 0. So now we're ready to do the second derivative analysis. So to start, let's find the second derivative. The second derivative is basically the derivative of the first derivative, and it seems like it is easier to differentiate the derivative if it's written like this. So we have 3x minus 2 times x plus 2, so we're looking for the derivative of that. And if I distribute everything and write it in standard form, then I end up with this. So the derivative of this is simply 6x. So to find where it's equal to 0 or doesn't exist, I would have to analyze the expression 6x, and again it's just a linear function, so it exists everywhere, so we're not concerned about the points where it doesn't exist, but it is equal to 0 when x equals to 0. And constructing the sign chart for the second derivative gives us the following chart. To the right side of 0 it's positive, to the left side of 0 is negative. So the function is concave down to the left of 0 and concave up to the right of 0. So at 0 we have inflection point, so we probably want to evaluate the function at 0 for the accuracy in graphing. So, but f of 0 is just the y-intercept, and we already know what it equals to. It's equal to 16. And now we have everything to graph this polynomial function. So let's draw the coordinate plane. And on the x-axis we're going to use this scale. 1 square corresponds to 1 unit. On the y-axis, since we have some large values here, I'm going to use 1 square for 4 units. Then we can label all the points that we found. So the y-intercept is 16, so it's right here, and the x-intercepts are here at 2 and at -4. Now we also have a relative maximum at -2. The function has a value of 32, and we also have an inflection point at 0, which is 16. Now, to label the end behavior, I'm just going to draw an arrow pointing upwards on the right side and pointing downward on the left side. And to sketch the graph, I'm going to go from the left to the right, and the function is increasing, and it starts at -infinity, passes through the x-intercept at -4, and then it's continued to increase concave down, reaches the maximum at -2, turns around while being still concave down, and heads towards the y-intercept, at which the concavity changes to the positive, but the function continues to decrease until it reaches the relative minimum at 2. There it turns around, so concave up, and from there it's increasing to infinity. So this is how we sketch the graph of a polynomial function using the first and second derivatives analysis.